Okay, lesson 34, implicit differentiation. If you recall, differentiation, another way to say, okay, we're going to take a derivative. Okay, with implicit differentiation, the idea is, okay, how do we take the derivative of something like this? Something that is implicit. When we talk about it being implicit, that means it's not in the form y equals and everything in terms of x. It's x's and y's multiplied together. And this implicit differentiation, we're going to use it when this is not easy to solve for y. And if you do get it solved for y, it's not a pretty equation to work with. Whereas opposed to what we're used to saying is, okay, if it's explicitly solved, y equals, then taking the derivative. Now, we don't know enough to take this derivative as is, if it is explicitly solved, because I haven't taught you guys quotient rule. We learned product rule, but we don't know quotient rule yet. So even if it is explicitly solved here, we can't do this. So how do we take the derivative when it's an implicit equation? That's what we're coming down to. So we're going to talk differentials. Remember the differentials? Okay, we learned about differentials, I feel like it was shortly before fall break. If you take the derivative of an x term, you have the derivative and then dx. If you take the derivative of a y term, you got the derivative and then a dy, right? Whatever, whatever the variable is. So that's what we're going to look at. Is we're going to take the derivative using differentials, and then our goal in the end, since it says find dy dx, is going to be to solve that equation and get it to be dy dx equals. That's going to be our final goal. So, are we ready for this? Am I ready for this? I don't know. Okay. xy plus 1 equals 2x minus y. Find dy dx. Thoughts on xy? You get to jump right into everything.
Do you have to find the derivative of x and then multiply that by y and then add the preferred x and then y?
Yeah. Okay, so as I said, we get to jump right in. Remember I mentioned product rule? xy is a product. That is x times y. There's a derivative of x, there's a derivative of y. But you don't just get to take the derivative of those and stick them together. We have to use the product rule. Product rule says take derivative of the one, keep the other. Plus, and then you flip-flop terms. Sound familiar? So the derivative of x is, derivative of x would be 1. And then we have to tag on a dx. I'm trying to think, how have I written this in the past? So how do I want to do this? So 1 dx, and then what else hangs around? Y. So I'm actually, because I get in the habit of putting my differentials in the back, how do you feel if I say 1 y dx? Because it's 1 dx times y. Now, you could drop off the 1 also, couldn't you? Okay. Plus, this time we're going to keep the x. And what's the derivative of y? 1. And then what are we going to say? dy. So I just wrote that as 1x dy. Plus, so that took care of xy because we had to use the product rule. What's the derivative of 1? 0. I'm just going to write a 0 because I'd already written the plus. Obviously, you don't have to write that 0. Okay? Derivative of 2x. 2. And then we're going to say dx because we're using differentials. Minus derivative of y. Minus 1 dy. Are we okay with that first step? Okay. Ultimately, at this point, my goal is to solve for dy dx. So my suggestion at this point is that we get dy's together on one side, dx's together on the other side. Because notice, with the exception of that 0, which we don't even need, everything has a dy or a dx, doesn't it? So let's work on doing that. I would say let's put our dy's on the left, dx is on the right. How much help do you need from me on there? So if I'm going to keep my dy's on the left, that means I am going to have to subtract 1y dx to the right. So I'm going to subtract 1y dx to the right. dy is going to stay, 0 is going to be gone. On the right, 2dx is going to stay because I'm trying to get dx's on the right. Minus 1 dy. I'm going to add 1 dy to the other side because I'm trying to get dy's on the left. So write out what you have there. What do I have? X dy plus 1 dy equals 2dx minus y dx. Okay. What do you notice on both terms on the left? There's a dy. So I can factor out a dy. Do you guys want to factor the dy out on the front end or the back end? Or does it matter to you? I normally do front end with most things except differentials. I tend to do back end. I don't know why. So I tend to, and we can do this either way. You can say, when we factor out dy, what's going to be left in the parentheses? X plus 1. And realize even if I didn't have that 1 dy written there as 1 dy, it'd still be a plus 1. And I'm going to put x plus 1 times dy. If you put your dy out front, same thing, right? On the right, we have a dx in common, right? That's the whole point we're trying to get to. Okay, 2 minus y in your parentheses. Dx is factored out. Okay, what is my goal for the left? I want it to be dy dx, which means, how do I move this dx to the right, to the left? We're going to divide by dx. Because since it's times dx on the right, to move it to the left, I'm going to divide it. Now, on the left, notice I've got dy dx, but I also have an x plus 1 hanging around. How do I move the x plus 1 to the other side? We're going to divide by x plus 1. If I divide the left by x plus 1, we divide the right by x plus 1. Does that make sense? I'm doing that all in one step. I'm assuming we're okay with that. So the idea is the x plus 1's canceled, the dx is canceled, and I end up with dy dx equals 2 minus y over x plus 1. Okay. Got a handle on that? Maybe? Kaylee's not sold on it yet. It is a little time consuming, but it's also one of those methods that we use when other things, traditional methods don't work. Implicit differentiation is not our normal all the time go-to method. It's a backup method. When the basics don't work for various reasons, this is a method we can bring in.
So this is the quadratic formula of this type of thing.
Kind of. When the basic easy factoring doesn't work, you had to go to quadratic formula. When the basic easy derivatives don't work, yeah. Okay. Example 2. Our given equation is y squared minus xy equals sine x. It's given that these are both x and y are functions of time. Find, and we're going to start with dy dx. So A is basically practicing what we just did up above. Okay? I want to see something. Did I put? I did. Okay. Grab my pen I just threw here. Set myself up to write at the bottom of the board, which is going to be annoying, but okay. Derivative of y squared. And I'm going to start over at the left so I have lots of room. 2y what?
dy.
dy. Minus.
dxy plus x dy.
What'd you say?
I said dxy plus x dy.
And how'd you get that so quickly?
Because I did the product thing.
Okay, you already had it worked out. I was going to say, or, based on up above, right? Now, here's the key you have to watch out for is it is minus this time, right? So this is a product rule again. It's x times y, right? So to review, we're going to subtract the whole expression. So derivative of x is 1. We're going to keep the y, and there's still going to be a dx. So I think, did Ross say dxy on that one, I think? Okay. And then, because it was subtracting this term, I'm going to, instead of saying plus in between, I'm going to say minus again. Because we're subtracting this whole quantity. And so now it's keeping the x. Derivative of y is 1 dy. And again, you can drop the 1's off. I probably should have. Equals, what's the derivative of sine x?
Cosine x.
Cosine x dx. Okay. My job is what at this point? Yeah, we want dy's together on one side, which my dy's are already on the left, so I'm going to leave them. I want dx is on the right, so I'm going to add y dx to the right. So then I end up with 2y dy minus x dy equals cosine x dx plus y dx. If you have not already, you want to factor out your GCS. So on the left, I'm factoring out dy. So I have 2y minus x times your dy. On the right, we are factoring out dx. So cosine x plus y times dx. Is this a little bit easier this time through? Okay, I know what to do. My goal is to set it up so it's dy dx equals, right? This is why I like to put my dy's on the left, because it sets me up to have dy on top there. So if dy is already on the left, how do I get dx underneath it? We're going to divide dx. Now that I have dy dx, I don't want this 2y minus x hanging here, so we're going to divide 2y minus x to the other side. And so now, it's writing your fun answer, which this is where I did not leave myself enough room. dy dx is equal to cosine x plus y over 2y minus x. Okay. B. What's B asked me to find?
Use with it.
Dx dy, right? We had dy dx. We need to find dx dy. Do we have to do all the work here? No. You can go as easy as saying, oh, well, if dy dx was that, then dx dy is going to be 2y minus x over cosine x plus y. You can just do an exact flip, and that saves me a little bit of time, doesn't it? And room, because I wasn't going to have room. And you guys don't want to work all those steps out again. Okay, C. dy dt is where we're at. Now, the odd thing is, this equation is in terms of x and y. There's not t's in here. But it does say as functions of time. That's the key right there, as functions of time. Easiest way to do this, if we're trying to find dy dt, we're still going to have to go through and use differentials, which means every time you see a y, take a derivative of a y, it's going to be a dy. Every time you take the derivative of an x, it's going to be dx. So we're actually going to start with this same first equation over here. And because we're trying to get dy dt, what I'm going to do is I'm going to take that same first line I had, and I'm going to divide every term by dt. So I'm going to write out my original equation was 2y dy minus y dx minus x dy equals cosine x dx. And the trick I'm going to do is I'm going to take each term, basically I'm going to divide the whole equation by dt. So I'm going to divide the first term by dt, the second term by dt, the third term by dt, and the fourth term by dt. If we're trying to solve for dy dt, we want to get all of our dy dt's on the same side. So I'm going to keep, I'm going to write this as 2y dy dt, and I'm going to keep my minus x dy dt. This minus y dx dt, how can I move it to the other side? We can add it to the other side. So I'm going to say equals, and I already have cosine x dx dt, and I'm going to add y dx dt. My goal is to solve for dy dt, so do you see where we're going here? Both terms on the left have a dy dt in common. So I'm going to factor out that dy dt. When I factor out that dy dt, I'm left with what in parentheses? 2y minus x, and I'm going to say times dy dt. Again, calculus habit, I'm putting my differentials at the back. I don't know if there's anything that says you have to, though. On the right, to kind of clean it up a little bit, both terms have a dx dt. And dx dt is just going to be part of the answer. We can't avoid that here. So I'm going to go ahead and factor that out. In my parentheses, I'm going to have cosine x plus y times dx dt. what do we do to get dy dt by itself? Divide by 2y minus x. And if I can fit it in here, so I'm going to have an answer of dy dt equals. Now, what I'm going to do is I'm going to go ahead and make cosine x plus y divided by 2y minus x a fraction. And I'm going to just put the dx dt at the end of the fraction. So I'm going to have this as cosine x plus y divided by 2y minus x. And then I just have times my dx dt at the right. I was going to say, do I use? I guess I do in my notes have parentheses around the main fraction. I'm not sure you'd have to have those parentheses around the main fraction, but I do. Okay. So make sure you have what you need there. I realize I'm not sure if Maddie could see what I was writing there at the end or not. So.
No, I just wait till you move.
I know. I try and, move back and forth. And
it's okay. Normally I know I understand what you're saying. So.
Yeah. Okay, you guys got what you need there? I think, if I recall, I just checked this. Did I put the next page? Oh, that's not the next. That's the back, isn't it? So I did not. Yep. Whoops, what did I do?
I don't know what right.
My Algebra 1 lesson for 7th period? That's Algebra 1 second semester. Okay, so I do need to go back and scroll that screen up, don't I? Okay. I was thinking I didn't need to scroll that screen up, but.
I was like, gosh, I remember when I got my X and Y.
Yeah, I remember when it was hard to remember that if you multiply two negatives, it was a positive.
Yes. Taking a test?
Yep.
Okay.
I told my younger self.
Okay, well, I have to find Levi's test here. Start working on example 3 if you haven't already. I'll catch up with you here in a moment. Yes, sir. Calculator for this home. So you can grab a ruler if you end up needing one. Okay. You're working on this, right? Should I go ahead and start my first line? When you did derivative of x squared y, did you use product rule? Derivative of x squared, 2x dx, and we keep the y. So I just wrote it as 2xy dx plus, now I'm going to keep the x squared. Derivative of y is 1, so just dy, minus derivative of y e to the x. Another product rule, yes? This time we're subtracting that product rule. So you either have to subtract it and put it in parentheses, or you're subtracting both terms. The derivative of y is 1 dy. So e to the x dy. Normally I'd say plus, but because it's being subtracted, I'm going to say minus. This time I'm going to keep the y. Derivative of e to the x is e to the x dx. Equals derivative of cosine x. Negative sine x dx. Okay, basics, right? Now we want dy's on one side, dx is on the other side. So I'm going to keep x squared dy minus e to the x dy. I'm keeping those on the left. On the right, I already have negative sine x dx. And I'm going to what? Subtract 2xy dx. And I'm going to add y e to the x dx. Does that match up with what you guys were doing? Stop me if I go too fast or if I do something astray. If you haven't already, and you might be getting to the point where you can do more of this in your head, just be careful, right? On the left, you're going to factor out the dy. So x squared minus e to the x times dy. On the right, factor out your dx. Negative sine x minus 2xy plus y to the ex times dx. And this is the point where I just write my answer. You realize hopefully what you're dividing on both sides. So I'm going to keep the dy here. I'm going to divide the dx over to it. That means my numerator is staying as negative sine x minus 2xy plus y e to the x divided by that quantity x squared minus e to the x. Okay.
Sergeant, what lesson was, how do we get the first half? Because I'm really confused on it.
On the product rule?
Yeah, what lesson was that?
I don't know. Is that the one lesson you happen to be gone?
It was the one we did like right.
Yeah, it was the one I was talking for.
31 was product rule.
Yeah.
And of course we're throwing in differentials right now, but the idea when you have two pieces multiplied together, you take turns. You take the derivative of one piece, keep the other piece, then plus, and then you flip-flop.
Okay, I get that part. I'm confused about why you use dx and then dy. Like why you multiply those to that specific one. I guess is what I'm confused about.
So the fact, let's see, on this one, x squared y. When I take the square root, when I take the derivative of x squared, it's 2x, and I took the derivative of an x term, so I said dx.
Okay.
And the y carried along. Then I reversed it, so now I'm keeping the x squared. The derivative of y is 1, and then since I took the derivative of a y term, we said dy.
Okay, that makes sense. I've been confused this entire lesson as to why we're using dx.
So whatever you're taking the derivative of, if it's an x term, you tag on a dx.
Okay.
If it's a y term, you tag on a dy. And so when we're doing that product rule, you have to pay it, what did I take derivative of there? Does that answer it?
Yeah.
Okay. Are we good? Okay. So you guys are good with that answer then? And we're ready to try example 4? Okay. Changing gears a little bit. Find the slope. Okay, so rewrite. Find the derivative. To find the slope of the line tangent to the graph of x squared plus y squared equals 2 at the point 1, 1. So, based on the fact this is x squared plus y squared, it's not solved explicitly to where it's y equals. We're going to use our implicit differentiation for the day. So, and I guess I'm going to say, we talked about slope, so we're going to find derivative. So what am I finding when I find derivative? We're going to be finding dy dx, right? So, derivative of x squared.
So 2x dx.
2x, and since it's an x term, we're going to tag on a dx. Plus,
2y.
derivative of y squared. 2y, since it's a y term, we tag on dy.
Is equal to 0.
Derivative of 2 is 0. Like what we've been doing today, we want dy's on one side, dx is on the other side. Me personally, I keep dy's on the left. Officially, it doesn't matter, right? So if I keep my dy on the left, 2y dy, that means I'm going to subtract 2x dx to the right. How much of this can you do in your heads? Or I guess I can show. What are we doing here? If we want dy dx, we're going to divide by dx. To get dy dx by itself, you're dividing by 2y. Now, okay, 2y's cancel on the left, and I have dy dx. On the right, what happens? dx is cancel and 2's cancel. So can you handle it if I say I'm left with negative of x over y?
And then since it's at point 1, you just plug 1 in.
Right. Yeah. So the slope of the whole equation, in other words, the slope of this circle, is represented by negative of x over y. We were specifically asked for at the point 1, 1, which in an ordered pair, we know that these are x and y. So yeah, so we're going to evaluate dy dx is negative of x over y, which is going to be negative 1 over 1, which is negative 1. That's because we plugged in our values there. I feel like this period's going super fast or I'm going super slow, and I'm not sure which it is. There's just a lot of work, I guess. Okay, example 5. Find the point or points on the graph of x squared plus y squared equals 2 where the tangent is horizontal and then where the tangent is vertical. Now, notice this is the equation from the previous page, yes? We already have done some work. What do you know about this equation? Well, at 1, 1, the slope is negative 1. In general, the derivative or slope is negative x over y or y over x. X over y. So that's information from the previous page, right? Why reinvent the wheel? Now, tangent is horizontal. So I mentioned earlier, did you guys catch? X squared plus y squared equals 2 is a circle, yes? It's a circle centered at 0, 0 with a radius that is square root of 2. Okay? Not that we really need to know that necessarily, but what does tangent is horizontal? So a tangent is horizontal, top and bottom of the circle, right? So tangent is horizontal. What do you know about a horizontal line?
It has only y values and no x value. Its equation is like y equals x something.
Okay, y equals a number. What do we know about the slope of this line?
0.
The slope of a horizontal line is always 0, yes? Okay, so think about this. What equation do we have for slope? We have that dy dx equals negative x over y, which equals what in this particular problem? 0. So then the question is, when does negative x over y equal 0? And we know that when does a fraction equal 0? When the top is 0. So this is going to happen when x equals 0. So at this point, think about your equation, because it said find the point. So we're looking for ordered pair answers here. Okay, x equals 0 is the x value. And so if we say 0 squared plus y squared equals 2. Solve for y, because we know what we know right now is we have the ordered pair 0, comma something. So y squared equals 2. If y squared equals 2, what's y? And square root of 2 and negative square root of 2. So what answers do I have?
0, comma, plus or minus square root of 2.
Yeah, 0 square root of 2 and 0 negative square root of 2. Or as you said, 0, comma, plus or minus square root of 2. Now, does that make sense, folks? Think about my picture over here. I had a circle, tangent line on top, tangent line on bottom. My circle is centered, dang it, caught my ankle second time today. My circle is centered at 0, 0. My circle has a radius that is the square root of this number, so square root of 2. So up square root of 2 and down square root of 2? Makes sense. Okay, because 0 square root of 2 would be this point, 0 negative square root of 2 would be that point. Okay. B. The tangent is vertical.
So this thing would be when y equals 0, and it's not a slope, right?
Okay, yeah. So we talk about when the slope is undefined or no slope. And that happens when 0 is in the denominator, right? When it's some number divided by 0. And so when you have 0 in the denominator, if you kind of do what we did earlier, and I said, okay, well, we already talked about dy dx is negative x over y. And so we want when there is some number over 0. So this time we are talking about when y equals 0, because 0 is in the denominator instead of the numerator. If you go through the similar work to last time, you kind of see where you're going to end up, don't you? So this time instead it's x squared plus 0 squared equals 2. So x squared equals 2, which means x is plus or minus the square root of 2. So you have the ordered pair square root of 2, comma 0, and negative square root of 2, comma 0. I didn't draw the picture like last time, but does that make sense? If you've got this circle, this time my tangents are vertical. Makes sense, it'd be square root of 2 over right and square root of 2 over left. Okay, one last part. Given that both x and y are functions of time and x squared plus y squared equals 2, find, first of all, dx dt, and then we'll use that in part B. So, in order to find dx dt, do you remember what we did earlier? You still kind of have to do your implicit differentiation, and you could use what we had on the previous page, but derivative of x squared is going to be 2x dx plus derivative of y squared, 2y dy, derivative of 2 equals 0. Since we're trying to find dx dt, we're going to divide each and every term by dt. So officially there are 3 terms you're dividing by dt there. Clean it up. And if I'm going to keep dx dt on the left, I'm going to say 2x dx dt equals, and then I'm going to subtract the other term over. So I'm going to subtract 2y dy dt over. If I'm trying to solve for dx dt, I need to divide by 2x. I should have done that differently. Oh well. Didn't make it very pretty. The idea is the 2 x's cancel, and we end up with dx dt equals, yeah, I really don't like how I wrote that. Why did I do that? Okay, we have a dy dt here, yes? And then we also have a negative 2y divided by 2 x's. Do you see that the 2's are going to cancel again? And so I'm going to end up with negative y over x. In that spot, I can't really write, times dy dt. Which I'm going to write over here in front of part B because we're going to need it, and you can't really read it there. So that says dx dt equals negative y over x times dy dt. Okay. On B, it says dx dt, find dx dt at 1, 1 when dy dt equals 7. Well, obviously, A and B relate because how else does it work? But if we're trying to find dx dt, we just came up with an equation, dx dt. What do we know about 1, 1? 1, 1 in an ordered pair are x and y values, and dy dt is defined to be, well, but dy dt is given here as 7. So fill in what you know, because you know everything. We're trying to find dx dt, negative of y, so negative 1 over x, so over 1 times dy dt, 7. So negative 1 over 1 times 7 works out to be nope, it's not going to let me. Put it over here. There we go. dx dt works out to be negative 7. Minus the technology glitches there. Okay. Lots of work with differentials there. That implicit differentiation. I wouldn't say it's not our go-to method, but it is an important method. So